Okay, welcome to the late night talk with the weird name. We're going to be presenting a targeted attack on an average company network. And what's going to be special about this attack is that we use lots of little bugs, which themselves don't really seem to have that much of an impact. But as we chain these bugs, as we put them together like the pieces of a jigsaw puzzle, you actually get a really dangerous kind of attack. So these are the things that we're going to be looking into. So we're going to do the entire thing. We're going to show how you get into the network, and once that you are in the network, before you can work all your layer 2 tricks, you'll probably have to bypass one filter or two, because just being in the network doesn't mean being in the network. You can land in different locations, and possibly you cannot reach the services that you want to compromise. In the end, we will then show how you can poison the Squid web cache in an attempt to control the entire HTTP traffic in the network. So this is the battlefield, and you're going to be seeing this throughout the talk, so you don't have to memorize it now. The only thing that's really important is that you are the pink bunny in the upper left. Apart from that, this is a very classical network design. Oh, one more thing. You're connected to the internet, and the network you want to attack is connected to the internet. Otherwise, this will just not work. Okay. So this is a very classical network design. What you have is called a DMZ. Basically what you do is you place all the services which directly communicate with hosts on the big bad internet into a separate zone known as the DMZ. And the rationale behind this is that if an attacker owns one of your machines which directly talks to hosts on the internet, then he's not yet inside the local area network, but just in the DMZ. He will still have to pass that internal firewall. So the question is, how do we get in? Well, due to the network design, it really does not make much sense to take the front door. And apart from that, you don't really have OpenSSH remote code execution in your pocket, right? Okay, all right, some may, okay. But if you do, you're probably not going to spend it on this network, right? Good. So there's actually another thing you can do, which is you can attack the clients. While they are not directly talking to to you, because they're using the web cache, they are processing an awful lot of data which you as the attacker supply. So if you look at the stuff that's on the client, you have this gigantic zoo of technologies all ready to exploit. So there's different media players, and then there's Flash, and you have different instant messengers, and entire desktop environments, antivirus, all that kind of stuff. So there's a huge attack surface for you. So you're probably thinking, yeah, just find some buffer overflow, some sort of memory corruption, and then that's it. We just own that box. Well, it's not that simple. It's not that simple because, first of all, how do you know what program the target user is actually running? So if you start spending all your time making that exploit work against Acrobat Reader, and then the person you're attacking actually opens this in XPDF, not good. And secondly, binary exploitation actually works very well when you have the binary that you want to exploit. You should know exactly how was this thing compiled. you know, what kind of, what version was this, stuff like that, so that you then actually know the addresses that you want to jump to. And once you know that, you still need to know what you actually want to execute. Because let's say you open up a bind shell in a network which is behind a network address translator. That wouldn't make much sense because you really can't reach it at all. So there is a sort of information gathering phase that we have to go through. And logical bugs often help you develop extremely stable exploits which do not rely on all of these little details for you to get that initial information so that then you can write your stable binary exploit. So what we're going to be exploiting is emoticons in Pigeon. So the admin in our network is Chatty, and he likes to use MSN on his Pigeon, and he has Linux because he's sweet. So for those of you who don't know, I hope there are some people here who don't know. These are emoticons. Somebody actually has to write code to make this work so that people can transfer these little images. What you see on the right is a body icon. That is something different. We're going to be exploiting that later. So right now it's emoticons. Okay, emoticons. In MSN, when you want to send an emoticon to someone, what you do is you say, I have these words here, best wishes, and whenever I type them, I want the other party to know that I actually want to send an image which is located at finger.jpg on my host. Okay? So now what the other party can do, and this is supposed to look complicated, what the other party can then do is say, I would like to request that emoticon. Because, you know, maybe the client doesn't even support emoticons, so then it would not have to request this. But if it does, it can. So this is a protocol, and it's very messed up, as you can see. It's basically a text protocol. But then you suddenly see that there are these parts of binary, the SLP header. And then as you look downwards, there's a base 64 encoded string. Base 64 encoded binary data. So you're thinking, like, you know, there was binary up there. Why again that we base 64 encode? Right, to send binary in a text protocol. But we were just sending binary up there, so that doesn't make sense. And when you decode this, you actually see that this is text data. But now, here's what's really important. You actually get to specify the object you want to download. Okay, so you again say, this is the location I want to fetch. What do? You go fetch something else, and it works. So here's the code. It's very easy. And what's interesting is that it really looks like if you were auditing a web application, you would be expecting exactly these kinds of bugs. But this is actually something just above layer 4. So you're looking for totally different things, and then you see this, and you're like, wow, this stuff works universally. Okay, so it's easy. Object location is fetched. We then just append object location to purple smileys, get storing there, and then we just send it. ADM is also vulnerable because it uses libpurple. What's really scary about this is you don't have to, you don't have to have the other side tell you there's an emoticon here for you. You can just download without it telling you. So you can silently download files off that system. Here's a mitigation step for now. You can remove the custom smiley directory. Then at least my exploit doesn't work anymore. So why did this work? I don't really think that this is just an implementation issue. This is really about a broken protocol, about a protocol which is so complicated even though it does something so simple. And then it uses these encoding schemes where it shouldn't be using them, and you kind of miss the bug because all you see is this base64 encoded stuff. And the funny thing is Microsoft actually messed this up as well in 2004. So that kind of, that shows the point. So you can download stuff now. You can download the binaries you want to exploit. You can now write your stable binary exploit. Nice thing is you can also query the proc file system. So if you're exploiting something that's already running, you can actually try to circumvent ASLR. You can also find out the proxy settings, and there are passwords lying around. You can download accounts XML, and who knows? Maybe there's a password scheme, right? So now, what do you want to execute? What's your shellcode going to be? Well, what you can do now is you can exploit body icons. You can actually send your patched version of Pigeon as a body icon simply by saying, this is my body icon. And then it will be stored on the remote system as a file, SHA-1SOM.icn for icon. And then now all your shellcode has to do is move that file to user bin Pigeon, and you have a patched Pigeon which maybe does stuff like, well, every message that comes from this and that user is redirected to the shell, and the output is redirected back, something like that. So that would be nice. About the memory corruption bug, we're not disclosing it here, but we're inviting you to play a game called beer fuzzing. Basically what you do is you meet up with friends, you get entirely wasted, and then you try to implement what I just showed you, the logical exploit, without copying from Wireshark. Whoever does not trip over a memory corruption bug in SLP code wins. Okay. You are now here. You are now inside the network, and on we go. What we now want to do is, ultimately, we want to attack the cache. But we want to be able to send anything we like to the cache, and there's still this internal packet filter. So that's what we're going to try to break. If you want to break something at layer n, it's always best to just look down a few layers and see if you can break things beneath. So what you want to break is on layer 3 and 4. It's IP-based packet filtering, basically. So why not go down to the link layer and see what you can do there? Well, we're assuming that these normal things, op cache, poisoning, MAC flooding, stuff like that, that all does not work. And in reality, it probably does, but let's assume it doesn't, because otherwise it's going to be boring. Instead, what we do is we want to attack the device drivers. So what could there be to attack with Ethernet device drivers? I mean, there isn't much there. It does addressing, error control, stuff like that. But then there's the MTU, and this is very interesting. It's the maximum. Wait a second. It's the maximum transmission unit, and this is the maximum size of a frame that you can have. So why would you specify something like that? Well, here's a problem. We actually share switches. So if you just tell people you can send frames as long as you like, then if you're the little packet and you have to wait for that big packet to just leave the switch, then that's going to take a long while. So that's probably a little voice over IP packet. Okay, so in the past, 1,500 byte, the MTU of Ethernet, made sense. Because in 10 megabit Ethernet, transmitting this took 1.2 milliseconds. But now we are 100 times faster. in gigabit Ethernet. So that means, of course, that we should adapt the frame size. And so we kind of did. We have jumbo frames now. The big problem is we also have those old frames as well, so we have a huge mess in our networks today. We have fast Ethernet NICs, those old 100 Mbit NICs, which can only do 1,500 byte. We have gigabit Ethernet NICs, which are capable of doing jumbo frames, but they actually don't. And then we have some which have them enabled, and then again we have some which have them enabled, but only up to 7,000 bytes or something like that. So it's a huge mess, and this is what we're going to attack. Because naturally the question arises, what happens if somebody sends a packet, a frame, which is 2,000 bytes long, to a destination which can only receive 1,900 byte frames? So here's what happens. Usually, if the frames are smaller than the MTU, each frame just gets put into its own little so-called RX buffer, the receive buffer. Now, if the frame is larger than the MTU, it will actually span multiple buffers. So this is not a problem for the controller, because the controller will detect that the difference between two frames, which were just where one was maximum size and the other was little, and one frame which spanned multiple RX buffers. Because between Ethernet frames, there's a tiny gap called the interframe gap. But the driver will actually have to handle the situation where you have a frame spanning multiple RX buffers. Do controllers handle this? Some do, others don't. Okay, so here's a bug we saw this year. It's the E1000, in the E1000 Linux driver, July 2009, and they actually proposed a fix. But the fix doesn't fix, and nobody's reported this, so now we're going to do that. This is the initial bug report. I'm going to read it to you. If we have a spanning packet, so one that goes across multiple buffers, the first part is discarded, but the second part is not. That one's kept. Okay. So now what happens is that if that second part is smaller or equal to 4 in length, we will then subtract 4 to remove the CRC checksum and actually cause an integer underflow. Then we get a bug. But actually, what's happening here? What's happening is that we're taking a frame and we're using the last part of the frame and interpreting it as an extra frame, as a new frame. This used to be payload, and now we're saying this is an independent frame. And that's the actual bug. So there's a cause. It's if we have a spanning packet, the first part is discarded, but the second part is not. And it is interpreted as an independent frame. Okay? And the effect is that if it is smaller than this and that, you get the integer underflow and all the stuff that we understand. So this is the code. There's a logical bug. The only thing that's important is the comments, which basically says, process the last fragment, and down there is the integer underflow. And this is the patch. Okay. So all they did was check whether this would be smaller than 4 bytes. Epic fail. They didn't even understand the bug, and completely misses the point. So Intel actually published an advisory on this, right? So you would have thought, hey, you guys have the documentation. You guys have the Ethernet nerds that made the driver, that made the card. Okay, so why did you not catch this? Epic fail again. What they did was they blindly copied Red Hat's advisory. Red Hat actually had an error in their advisory. They said, E1000 causes panic when changing MTU under stress was the fix that would fix this. Now, obviously that has nothing to do with the issue, and now Intel chooses this as the title of their advisory. So we get a free ODE. And before I forgot to tell you about the ODE clown. The clown you see up there, that's the clown you will see whenever we publish an ODE, because for me this kind of symbolizes the feeling you have when finally, after months of work, something actually works. So, yeah, what you can now do is you can piggyback your actual frame, the frame that you once sent to the destination, inside a large frame, and then the first header will be checked and the second one will not be. So we get to pass through the firewall. There's a slight difficulty with this, but it's not really a difficulty. The CRC checksums must match, but since we have this part of the packet which can be discarded, we can actually put whatever we want into there. And if we can set 4 bytes arbitrarily, we can just adjust the checksums. So this is not really a problem. It's not MD5, it's CRC32. There are limitations. Default MTU, it does not work, but for all other MTUs it does work. So, now we've bypassed the firewall, at least in one direction. And now we can go and attack Squid. Next goal, we want to be able to supply updates from update.adobe.com or provide the start page for citibank.com, something like that. Poisoning the cache. What's the time? Ooh. I'm going too fast again. Okay, poisoning the cache. The interesting thing about the Squid web cache is that it's actually not just a web cache, it's also a DNS cache. This gets obvious because you can actually tell it to get foo.bar and not just to get some IP address. So it caches DNS for a max of 24 hours, so that's enough for us to want to attack it. And the authentication used for DNS has been criticized over and over again. Those are just 32 bits, really, which we have to guess. There's the source port, the UDP source port, which is not even part of the DNS message. And then there's a transaction ID. So now, even in the face of popular DNS security research, Squid chooses to implement this by itself. And what it does is it opens a single UDP socket to transmit all DNS queries. Okay, so this is random. This is a random port. That's nice. But it's static. It remains the same over the entire lifetime of the cache. And that's not a wise choice, because by default, you can actually scan for this. Because if you send the UDP datagram to a closed port, you get an ICMP port unreachable by default. Otherwise, you just don't get any response, so you can see whether the port is open or not. But of course, we're assuming that we can't do this. Because if we assume that we can do this, which we probably can in reality in many networks, then it's going to be boring again. So we can't do this. So here are the implicit assumptions Squid is making, and this is actually the interesting part. See, first of all, Squid is protected from IP spoofing if layer 2 and layer 3 actually provide this. Then Squid also expects that you filter ICMP port unreachables, because if you don't, the source port's scannable. And then it generates its own transaction ID of 16-bit. And that's all the security provides itself. So trust, the security is actually handed off to other layers. And that's the dangerous part. So for the attacker, it looks like this. We need to bypass layer 1 and 2, layer 2 and 3 filters. Done with the Ethernet exploit. Now, we need to determine the source port. even if we can scan for it. And that's what we're going to do now. So to do this, we break the nut. Because you cannot assume that the source port will actually stay the same if your packet is transmitted over a network address translator. So here's what it normally looks like. Normally, you have your internal IP address, 192.168.2.3, and then it's mapped to an external IP address, 80.80.80.80. And the source port stays intact. There's no reason to change it, simply. But now what happens if two different hosts inside the local area network want to use the same source port? Well, for one of them, it's not a problem again. The IP address is mapped, but the port remains the same. But for the other, we have to do something. We have to kind of handle the collision that arose. And we do that by using the static port 1024. But that's not the bug yet. So, first part is the collision, which is handled correctly, like I just showed you, the first two rows. And now the bug. If you now send a packet on that same source port, but to another host, to a host somewhere on the internet, it will actually handle the collision even though there is no collision. So now it discloses that there was a collision earlier. It tells you that the source port was actually already used to connect to the DNS server. So how do you exploit this? I know this is not that easy to understand on the first explanation. So this is how you exploit it. Maybe this will be clearer. First, you send a packet to the DNS server with a given UDP port, the port that you want to scan, source port. Now you send a packet to that other host that you control on the internet with the same source port. And now at that other host, you can check whether the port is the original port or 1024, in which case this port was used to contact the DNS server. So this is how you can scan the nut for the source port used by Squid. All right, done. Last step. We need to reply with the correct TX ID before the DNS server does. I'm going to show you one possibility which actually did not work out, but it's so beautiful I just can't leave it out. This is a design bug, kind of. It can work, but not with default configurations. What Squid does is really funny. When it is waiting for a DNS response, it will constantly call receive from, give me the next packet, please. But when it's not waiting, it will just sit there and sleep. And you can fill the queue. So you can place your guesses in the queue before the race starts. Yeah. I will gladly store your guesses in kernel memory until the race begins. First thing into the race will consider your guesses, sir. So the default queue size, at first looks pretty big. So you start calculating and writing down stuff, and it's like, oh, I do 20 tries, and I'm at 50% chance without knowing anything. But in practice, that doesn't work because of all of the overhead you have. This queue actually stores complete frames because, of course, when you receive frames, you don't really want to do a lot of copying. So in the end, you end up with 50 DNS responses you can place in the default queue. So that's nothing. You can't work with that. So I tried to determine that upper bound. I wanted to know how much can I place in practice by sending header-only packets, which then gave me this DOS for free. So you're stuck. It's right before Christmas and you're stuck. But then you realize that there's a huge difference between guessing correctly before the DNS server does and guessing correctly in the time frame it would normally take the DNS server to respond. Because who tells us that the DNS query will actually reach the DNS server? If it doesn't know about the query, it will not respond. So what does Squid do then if there's just no response? It will wait for 2 minutes. And 2 minutes is enough time for us to just put all guesses in the queue and just guess them all. So all we have to do is kill this firewall. So, okay, you could say, you know, you placed that Ethernet adapter, and of course I did. I mean, this is my story. But there are lots of ways that you can make the UDP datagram drop. But I really want to present this other Ethernet bug as well, so we're going to be using that. Writing unique drivers is hard. Why? Because you actually have to support all sorts of different hardware which have the same name, but they're slightly different, and then they have slightly different bugs, but you have just one driver. And you cannot get documentation for it even if you, I don't know, sell your soul to the devil or sign a non-disclosure agreement. And sometimes this whole business of writing drivers seems like an experimental science when you read the mailing lists. So this is what the driver maintainer says, and I love this quote, so I put it on the slide in full. He says that the RX mux size register does not work as expected, and incoming frames whose size exceeds the MTU actually end spanning multiple descriptors. So this is the same that we saw with E1000. If you have a frame that's longer than a buffer, it will just span multiple buffers. That's it. But what's different about this card is that the length field, which will be reported, is going to be the length field of the entire frame, and not just that of the one in the buffer. So you right past the end of the buffer, you just allocate it and you get memory corruption and it's all bad. Or there's some garbage in the size field, but we're going to come to that later. Okay, so he proposes a patch. He says, first of all, I would like to disable hardware filtering because so far it only proved to be able to trigger some new fancy errors. Secondly, drop all multi-descriptor frames. Anything that is in more than one descriptor, he actually means buffer. Anything that's in more than one buffer, just drop it. We're not handling this. Okay, so this is the change. Instead of saying the maximum size that you may receive is RX buff size, which means enable hardware filtering, just tell it, you know, receive anything, disable hardware filtering. Well, in 2009, adapters seem to be different. What was actually found out is that RX mux size with these new adapters is not the size after which hardware filtering is enabled, but it's actually the size the adapter thinks it can copy into the buffer. So they made that check, so they patched it back. So wait, I'm going to go back a slide. That's not good style, I know, but look. Minus, plus, plus, minus. So now hardware filtering is enabled again. And remember François' words, so far it only proved to be able to trigger some new fancy errors. And that's something we're going to be using. So what we did was we did MTU scanning, meaning we just sent frames of all possible MTUs to the adapter, and we just see whether something weird would happen or not. And we found out that when you send a frame of exactly RX mux size bytes, then the adapter will show some really fancy errors, as François put it. It will actually report that it has received multiple multiple fragments of a frame, and each fragment is 8,000 bytes in length. So that can't be, due to the Ethernet spec. You can only have 9,000 bytes, so that's obviously some kind of bug. And then device and driver lose sync, because the device is just reporting garbage. And now the RX buffers contain old frame payload. When you send new packets, the RX buffers will actually contain old frame payload. But what's more important is the RX descriptors, the meter data, the length field, the status, all of this contains old frame payload.
Very nice.
So there are two paths in the receive function, and they are both completely controlled. Well, the path we take is completely controlled by the status register. And we completely control the status register, so we completely control the path that we're going to be going. And there's one path which is the reset path. And when you hit the reset path, everything goes back to normal. Everything's good. It's like nothing happened. When you hit the receive path, some junk will be handed upward instead of the packet which actually arrived. So now what you can do is, since we control the status register, we started writing proof of concept exploits which would basically just spray the RX buffers with some value so that that is then transferred in the status register. Then we would send the offending frame, meaning the frame with that length of RX mux size, and then send a ping to get an RX interrupt triggered so that this would actually be handed up. Now if you spray with A's, something nice happens. You get a complete frame of A's of size 317 handed upwards. Now 317 is 321 minus 4 for the checksum, and that is in hex 0x141, which is, well, they apply a mask, so it was originally 0x4141, which is AA. Okay, so that's our payload. When you spray with E's, you hit the reset path. And now when you spray with A's first, and then with E's, you actually get to drop N frames, some amount of frames you want to drop, and then the adapter goes back to normal. That was the elegant case of making sure that the DNS packet, the DNS query would never reach the DNS server. Here's a brutal case, I like this a lot more. The brutal case, you spray zeros, so then you get a packet size of -4. And then you need to pass that first check, and you do pass the check because these are both signed integers, so it's a signed check, and you'll just see, oh, packet size is -4, and RX copy break is, I don't know, 1000 or something like that, and you pass the first check. So then you go down to the allocation of the buffer, and you think, oh, I'm never going to pass this check. Net IP align is actually 2, so packet size plus 2 will be -2, and when we cast to unsigned, it will be, just huge number. We can never allocate this, so it will never pass this check down there. But we really wanted to pass that check. And we're lucky because it does padding for us. So it will add 32 more bytes. So then it says allocate 30 bytes, so we get to pass the check. And then we copy just huge amounts of data into, 4 gigabyte into your kernel memory. And it's a beautiful crash, and it's an interrupt context. And I wish there was a haiku about blinking keyboard LEDs. The attacker's view, we're done. So I actually have a point, and I have time to make it. Here's what I want to say. The security of a network component depends on its environment. You shouldn't, Squid is a really good example, because Squid basically places all of its security into the hands of other components, other layers, and it then gets exploited because we exploit its environment, really. And then when you do a targeted attack, the nice thing is often when you just do some generic attack and you're just targeting anything, your exploit will not work because of some little detail of the network. But in a targeted attack, you can actually make use of this little detail in the network, and that's different. And finally, vulnerabilities do not live in isolation. You see, many of these bugs were just little bugs, but as we chained them, they were really powerful. So it's hard to determine the impact of a vulnerability before you've actually seen how somebody puts the vulnerability to work. Thank you. So we have 20 more minutes for questions, if there's anything. Okay, I mean, you can talk to me later. I'll be here the entire time.